and we'll call that base b, is defined by the equation f of x equals b to the power of x, where we know that our base b does not equal 0, and x is a real number. All right, so let's say if we have, for example, we wanted to graph f of x equals, that should be 2 to the power of x. Let me make that 2 a little bit bigger. Here we go. Okay, so we can start off just by making a table. Okay, well, this is your x, and this is your f of x equals 2 to the power of x. And yeah, that'll work. Okay, let's say if we go -3, -2, -1, 0, 1, 2, and go 1 more to 3, just to keep it symmetric. Okay, so we know that 2 to the power of -3 is just 1 over 2 to the third power. I'll actually give that a little more room so I won't have to squeeze everything in there. There we go. And 2 to the third power is just 8, so we have 1 over 8. So we can go ahead and graph that. Let's say 1, 2, 3, 4, 5, 6, 7, and make that 8. -1, -2, -3. Okay, so we have the ordered pair -3, 1 over 8, which let's say is about right there. Probably a little lower, but we'll just put it right there. Okay, when x is equal to -2, you have 2 to the -2 power. Remember, that's just 1 over 2 squared, which is 1/4. So when x is -2, y is 1/4, which goes up just a little bit. When x is -1, you have 2 to the -1, which equals 1/2. So it goes up a little bit more. It's probably not lined up the way it should be, but hopefully you get the idea. When x is equal to 0, you have 2 to the 0 power. Anything to the 0 power is just 1. So you end up right there. When x is equal to 1, you have 2 to the first power, which is 2. When x is equal to 2, you have 2 squared, which is 4. So 1 is 2, and x squared is 4. And 2 to the third power is just 8. Okay, so you end up with 2 to the power of x looking somewhat like that. Okay, so let's say instead we graph our f of x equals 1/3 to the power of x. we start off the exact same way. But instead of -3 to 3, I'll just go from -2 to 2. So our x and our f of x equals 1/3 x. So -2, -1, 0, 1, and 2. And that ought to be enough room. Okay. So if x is equal to -2, I have 1/3 to the -2 power. Remember, that's just 1 to the -2 over 3 to the -2, which means that negative exponent goes down, that negative exponent goes up. It's just 3 squared over 1 squared, which is just 9. All right, so we can go ahead and make our graph. We go from -2, -1, 0, 1, and 2. 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so when x is -2, y is 9. We can go ahead and fill that in. When x is -1, we have 1/3 to the -1 power, which ends up giving us 3 to the 1 over 1 to the first power, which is 3. So we have -1, 3 when x is -1, y is 3, so we can go ahead and fill that in. Same thing with 0. We have 1/3 to the 0 power. That's just 1. Anything to the power of 0 is 1. When x is equal to 1, you have 1/3 to the first power, which is just 1/3. And when x is equal to 2, you have 1/3 squared, which is 1/9. So it's a little bit lower. So give or take, it's about right there. So if we go ahead and connect those, yep, we can see that when our base is bigger than 1, it's increasing. And when our base is less than 1, it's going to be decreasing. All right, bring that up a little bit. All right, and that brings us to our in general. When your base is greater than 1, an exponential function clean that up a little. Is an increasing function. Okay, and we saw that for f of x equals 2 to the power of x, where we know our base is equal to 2. But when our base is less than 1, or you can say between 0 and 1, an exponential function is a decreasing function. And we saw that with f of x equals 1/3 to the power of x, where in this case our base was equal to 1/3. Okay, so now we're going to look at what they call the natural exponential function. Okay, so what if we have the number 1 plus 1 over n to the nth power? And we know that it approaches 2.71828 as n gets bigger. Okay, so let's say if we decide to have this column as our x and this, make that a little bit bigger. And I'll make this bigger also, since some of those values are going to grow pretty quick. And let's say, well, instead of x, forgot I used n this time, so we'll make that n. And 1 plus 1 over n to the nth power. Okay, so let's say if we decide to make n equal 1. You have 1 plus 1 over 1 to the first power, so you have 2 to the first power, so you have 2. So you decide to make n equals 2. 1 plus 1/2 to the second power, you plug that in, you end up with 2.25. Say you make n equal 4. 1 plus 1/4 to the fourth power, you plug that into your calculator, you end up with 2.414, and it keeps on going and going and going and going and going. Say you make n equal 12. 1 plus 1 over 12 to the 12th power, you plug that into your calculator, you end up with 2.61303, and it keeps on going and going. Okay, let's say if you let it equal, n equals 365. Plug that into your calculator, you actually will end up with 2.714567, and it keeps on going forever. So let's say if you plug in 100,000. Okay, plug that into your equation. As soon as you plug it into your calculator, you get 2.718268, and it keeps on going. Okay, so let's say you plug in 1 million. You'll end up with 2.7182837. Oh, didn't need that decimal there. And it keeps on going forever. And we can just keep on plugging it in, plugging it in, and plugging it in. And as you just make it 1,000,000, 5,000,000, 1,000,000,000, 1,000,000,000,000, whatever you make it, it'll just keep getting closer and closer and closer to that value. So 2.718281828, and it keeps on going. We just make that E. So when you see that E in your calculator, that's all it is. Okay, so f of x equals e to the power of x is your natural exponential function. All right, so any questions on that one?
We're not going to have something like that, and it's just because we're not using the calculator.
Oh, no, you won't have anything like that. Okay, and we're going to use this to solve exponential growth and decay problems. And I'll leave that up for a few more seconds.